All right, so I'm going to work a couple of different problems. Most of them will be trusses today. If you have something else that you want to work on, we can do that. Eventually, we'll move on and we'll do like next one we'll start on centroids, and we'll do a couple on centroids because centroids are going to be pretty important moving forward. So I apologize for any noisiness here. I have no power at home. I'm just saying this for the recording, but I have no power, and so I'm at this coffee shop, and of course my dog is running around, and who knows what's going to happen. Anyway, so this is the problem actually that I used for the opening of what do you call it? This is actually the image on the cover of Moodle for you guys. Is this problem right here? And what the problem is basically is it says this is what you're given, and what it wants to know is what is the tension in all three cables. And so I'm going to tell you right now that without even solving this, the tension in one of these, or I know the tension in one of these, and I hope that you can get enough intuition that you would know the tension in one of these. Do you have any idea which one you might know the tension in, or what it might be?
B maybe, because B and A and on the same side, so we can start from there.
Yeah, maybe, but that's not what we know. So here's what I want you to do. I'm going to draw this exact same picture, but I'm going to draw it from straight above. All right. So like if you're looking straight down the y-axis, so from straight above, it looks like this. And you've got A going off this way. And you got C going off this way. And then you going off this way. Hannah, just speak up. I can't answer chats right now. Okay, that's 60 degrees. So can you see?
I was just asking if it was centroids.
No, I'm not going to do centroids today. I'll do centroids, I think tomorrow and then the following Monday. I'm going to do some more trusses. But first I wanted to do this one that's really just an equilibrium problem, but I thought it kind of ties in with trusses pretty nice. Can you tell, Hannah? I mean, I don't know if you were here a second ago, but what I'm asking.
No, I just got here.
Can you, from looking at, okay. So what I'm asking is, what we're going to do is we're going to solve for the tension in A, B, and C, and these cables that are holding up this big block. I guess I have to give a weight for this block. Let's just give it 500 newtons. It doesn't matter. Say that that's how much this thing weighs. Okay, so can you tell what we want to do is we're going to solve for the tension in all of these. And what we're going to do is we're going to set up the equations and we're going to go ahead and solve them. But what I want to know is just by looking at it, can you tell one of these is if you're good at statics, you can if you already had the class, you could look at it and you could tell right off the bat, one of these, the tension is very obvious. And you have to use your mindset from trusses. And so if I draw these from above, so I just drew what's going on here from above. So to be clear here, this 15 degrees right here, that is in the XZ plane. Or excuse me, this line right here is in the XZ plane. So this is 15 degrees above that XZ plane. Okay. And so if we look at it this way, hopefully it's obvious to you guys that C is in the X direction. A is in the negative X direction. And so if we sum forces in the X direction, right, we're going to end up having AX plus CX, or negative AX, I guess, plus CX. And then we've got, a BX, right? We've got some component of B, right? So I'll say minus B in the X direction equals 0. Okay, no problem there. What about in the Z direction? So this is the Z direction right here. Sum of the forces in the Z direction equals 0. Well, you'll notice that we only have one force in the Z direction, and that's B in the Z. And so B in the Z in this case has to be equal to 0. And this is the exact equivalent of having a 0 force member. So notice that if B had any force on it at all, then AX and CX, because they're in the X plane, they can't resist it. You know, they can't resist it because this thing is, some portion of this is going to pull in the Z negative B. So basically, you know, B cannot do anything. So this is the equivalent of having a zero force member. Okay, it's the same idea as when we were looking at trusses, and you've got, sorry about my finger slip, but you got some member like this, and you've got another member that comes in like this. Well, this member right here, it is a zero force member, because if it pushes in the X, if it pulls, excuse me, it pushes in the Y or pulls in the Y, then it in this joint in that direction, but these are only acting in the X direction. So in other words, this has to be a zero force member. So same thing is going to happen over here. That entire B is going to be a zero. Okay. And of course, we just solved that. But mentally, hopefully you can see where that came from. And if I were to give you a problem like this one, you could go right off the bat, you could say, okay, well, B is zero. And once B is zero, this becomes a two-dimensional problem instead of a 3D problem, which is much harder. Okay. So what we'll do at this point is, you know, I've got these three forces. I've got my sum of forces in the X. I've got my sum of forces in the Z. And we'll go ahead and get the sum of the forces in the Y. And that, of course, is the hardest, because AX is positive. Excuse me, AY is positive. BY is positive. CY is positive. And then this 500 Newton force is negative, and all that adds up to zero. Okay, at this point, we need to start doing some trig. And this is, I'm going to do this relatively quickly because this is, at this point, old hat for you guys. You know, I really just wanted to kind of, you know, point out this, the zero force member, and how it can help you, you know, on pretty much any problem. So because B is a zero force member, I can get rid of this right here. A in the X, well, that's going to be A. Is that A? So that's this portion right here. So that's A cosine 10 degrees. Okay, plus CX, that's C cosine, because that's this portion right here, 15 degrees equals zero. Okay, down here, BY goes away because there's no B. So AY, that's this portion right here, that's A sine 10 degrees, plus C sine 15 degrees, because that's this portion right here. No, sorry, not that's this portion right here. C sine 50 degrees. I'm gonna go ahead and bring that 500 over to the other side. Okay, and then just to solve this thing right here, I could say C equals a cosine 10 degrees divided by the cosine of 15 degrees. I actually don't have a calculator on me, so in this one we're going to solve kind of wonky like that, but it's okay. So here we go. So if I had a calculator, I could plug that in. I do have my phone, so maybe for more complicated problems we'll get numbers, but for this I'm just going to take that, I'm going to plug it in down here. So I've got A sine of 10 plus A cosine 10 over cosine 15 times the sine of 15 equals 500. Okay, so now we end up with some big ugly thing that no one wants to deal with. So A equals 500 newtons divided by, it looks like it's going to be sine of 10 degrees plus cosine 10, cosine 15, sine 15. Okay, and that's how we get A. Let me go ahead and see if I can plug that into my phone. Let's see here, calculator. Phone calculator is so wonky. Cosine 10. Let's see or something. Let's see what setting it's on. Cosine 45. Okay, it's on the right setting. Cosine 10 divided by, it's really noisy here, I apologize. Cosine 15 times the sine 15 plus the sine of 10 Okay, let's put that on the bottom by raising it to the -1. Let's multiply by 500. You can pet him. He's nice. His name is Rocky. Okay, and so we get, sorry, we have kids petting the dog. Okay, so we got 1,142.8 newtons is A. Okay, and we can plug that in right over here and we'll get C. And C equals, we'll take that number, multiply by the ratio of the cosine of 10 to the ratio to cosine of 15. And we get 1,165.1 newtons. Okay, and so if we round that to 3/6, we say A equals 1140 newtons and C equals 1170 newtons. Okay, so this problem I gave on a test a while back, not a while back, last semester. And some of my more intuitive students noticed that this was a zero force member and they were able to save themselves some work. So it's just something that I wanted to point out. Anytime you have a force that is the only force in some direction, it's going to have to be zero because otherwise things can't sum up. Okay, so any questions?
So it's like a redundant force?
What's that?
So it's just like redundant?
Redundant would be the wrong word. It's more like the like, for example, one of the ways there's no such thing. I think Jeff Hansen did a video on this, but there's no such thing as you can pet him. He likes pets on his belly, but he wants to give you a kiss too. So you have to, he might lick you. Okay, so one of the things is, this idea of a straight rope, like you can just keep pulling on a rope, and if you keep pulling and you keep pulling and you keep pulling, you get the rope completely flat. And that's true if the rope has no weight. As soon as the rope has some weight, then what happens is you've got a downward force here. And the only way to resist that, so if we go in the Y direction, the only way to resist that downward force is if there's an upward force somewhere. And if these forces are both to the right and the left, then they can't resist this upward force. And so what ends up happening is no matter how hard you pull in on these two ends, there always has to be a little bit of a slope to it. So you have an upward component here resisting this downward force here. And so the same thing's going on here in that, if I have these two ropes and they are, because the problem tells us they're in the X direction, then this force, the Y component of this B right here, it's got nothing to resist it. So the B basically can't exist. So this whole thing goes away. Does that help, Stephanie?
Yes.
Okay, right. So it's I don't know. I mean, I spent a certain amount of time kind of like staring at these sometimes going, is that a zero force member? Is that a zero force member? And so what you're looking for is basically it's the only force in a direction. So even though we always think about this as X and Y, and usually, you could also have these on angles. So even if I'm working the whole problem in X, Y, I can easily have a truss that looks like this. And it's got another member coming in off of it like this. And the thing is, at least temporarily, at least mentally, I think, okay, here's one direction. Maybe it's not X because maybe I'm working the rest of the problem with this as being X and this as being Y. But for right now, I can think of this as X prime. And this thing has and so this then is like Y prime. And this member right here, it's got some portion of it that's in this kind of Y prime direction. And this member right here cannot resist that. So that means that this is a zero force member. So sometimes you just got to kind of mentally like turn your screen or turn your head and think about it a little bit differently. I don't think I like teaching from coffee shops. It's really noisy. It's giving me a headache. Anyway, so that's the idea. And that was kind of why I wanted to do that one today. And then how much do you, so I was going to go to the practice problems, and I think I assigned this one too, and I had a number of questions about this one. So I think I wanted to talk about it's a problem. Let's see. So on the practice, it's problem number questions 11 and 12 from the practice, and so it's a truss. And I just kind of wanted to work this one. I can't have any. Oh, they want the force in every member of this thing. So I wish I could bring this one up on my screen because it would make for a much neater drawing. But let's see. So we've got this truss, and I'm going to draw it quite large because we're going to do our work on the truss. Okay, so we've got a pin connection here. We've got a roller here. Okay, and hopefully you guys realize at this point that the reason they give you the rollers is because the rollers help them to figure out, the rollers help you to solve the external forces on the structure. So this is P, and on my screen, this is an 8 kilonewtons. And then there's a 10.5 right here. There's a 10.5 right here. It looks like we've got this. Okay, the annoying thing about this one is it has a lot of weird angles. And we don't really like weird angles if we can avoid it. Okay, so let's see. So this is A, B, C, D. This is E, F, G, and H. Okay, force downwards, 5.7 kilonewtons. Okay, so what we're going to do here, oh yeah, we need some, so this is 3.8 meters. This is 3.2 meters. 3.2. 3.8. And then it's 2.4 all the way to here. Okay, so the annoying thing about this one is, well, we've got some unusual like angles. And so it might be good, for those of you who, like to work with sines and cosines. I like to work with similar triangles. But if you like to work with sines and cosines, it might be beneficial to right off the bat just try to start like knocking out some of these angles, because you're probably going to need this angle, you're probably going to need that angle, right? And it's symmetric, so that's kind of nice. And our forces are symmetric. So if you see a completely symmetric system, one of the things I recommend to you is right off the bat to just go, you know what, I'm only going to solve one half. Once I solve one half, I know the other half, because there's no reason that either half would be different. And you can do that, okay? You can just, as long as it's completely symmetric. The only place that might give you pause on this one is the fact that this is a roller and this is a pin. But if we, do the sum of forces in the x direction, we're going to realize that this force is 0. AX is 0. So we're not really going to worry about that too much. So let's go ahead and get those external forces, and then we'll get those angles. Sum of forces in the x equals 0. We've got AX is the only force, so it equals 0. Okay, so that makes our life easier. And then the y direction, sum of the forces in the y direction, well, that's a little bit more complicated. It looks like, let's see here, negative 5.7, negative 10.5, negative 8, negative 10.5, negative 5.7. So what's that? These two add up to 11.4. Let's see here. So negative 11.4 minus 21 minus 8 equals, oh, wait, sorry.
I like whatever I moved.
Plus AY plus HY equals 0. Sorry, there's no newtons in here only because I'm out of space. So that's 29, 40.4 it looks like. So AY plus HY equals 40.4 newtons. Okay, and in some ways maybe that wasn't the best way to do this, because if we sum moments, this is going to solve itself. We just have to pick a point. We always like the point with the pin, because that gets rid of the force. and half times its moment arm, which is 3.8. Okay, and that looks like that's going to be going in that direction. So that's clockwise. So that's negative. Okay, minus 8 kilonewtons. Oh, these are kilonewtons. Sorry about that. These are all kilonewtons. Kilonewtons. Okay, and that 8 is the same direction. And that's going to be times 7 meters. And then we'll go minus 10.5 newtons times, in this case, that moment arm is 7 plus 3.2, 10.2 meters. And then we've got that 5.7 minus that 5.7 kilonewtons times, what's that going to be, 14 meters. And then all that's going to be being resisted by this H, I guess I'll call it HY. It's really the only H there is, times 14 meters equals 0. Okay, so once we have all that, plug and chug into the calculator. Some of you guys have, let's see here, 10.5 times 3.8 plus 56 plus 10.5 times 10.2 plus 5.7 times 14 equals 282.8. We're going to divide by 14, get 20.2. Is that right? Yes. HY equals 20.2. And of course, we should have known that actually. Because this is symmetric, we should have known that HY and AY were going to be the same. So basically, half of that 40.4 had to go to each one. Okay, so if I plug this in up here, AY equals 20.2 as well. Okay, if we gotten any other number that wasn't symmetric, we should have worried greatly. Okay, so that's the beginning of a lot of these problems, is just doing the reactions. It's not necessarily the part that we love the most. So I just want to have forces here. I don't want to have any of this other nonsense. So, all right. And that's actually one of the things that I, like to have in these problem solving sessions is, moments where I can give you kind of what I see, so that hopefully you can start to see it. This idea of symmetry. I remember the first 8 times I saw a professor do it, I thought, you can't just do that all the time. And you can do it all the time if it's symmetric. If there's absolutely nothing different between the sides, you can just assume the solution to one side is the solution to the other. All right. So now we want to work through this thing. I'm going to do this with angles because I think most of you guys are more comfortable with angles. So let's just go ahead and do that. Now, what this problem wants everything. So this is given. Required is everything. Okay, they want do a clever cut on this thing and then solve it. There's no cleverness. There's just a lot of work. So let's go ahead and get this angle right here. I don't know if I want to call it. Maybe I'll call it theta 1. I'll call this theta 2. So theta 1 equals the inverse tangent. And so I have to figure out something that's going to define this angle. The problem is I don't know how far it goes up right here. Okay, now if this were 3.8 and this were 3.8, those were the same number, then I could say it went up half of the 2.4 by similar triangles, but they didn't go up the same amount. So I could do some similar triangles there, but I'm not going to bother with that. I'm going to say that it goes up the full 2.4 meters. Okay, while it goes, so this is my triangle. The hypotenuse, sorry, not the hypotenuse, the opposite is this 2.4 right here. And the adjacent is this 7 right here. So we're going to do 7 meters right here. Okay, and that angle. Okay, no, inverse tangent, please. Inverse tangent of 2.4 divided by 7 is 18.925. 18.9. Hey, there's no need to bark. You guys made a friend. He demands love. 9 to 5 degrees. And we'll do the same thing for theta 2. Theta 2, though, here's our triangle. Okay, the opposite is still 2.4. Hey, we're in a public place, my boy. You don't get to bark like that. Okay, and the adjacent is 3.2. Okay, so this is going to be much closer to 45. Noting in your head that this ratio, if its ratio is 1, you're going to get 45. Okay, so so it's just kind of, I don't know, something to think about. 2.4 divided by 3.2. So we're now at 36.870. Okay, so we can put those. I'm going to go ahead and put those here because that's going to, while it might get messy, it's going to open up some space for me to work. 18.925. Okay, so assuming that we've done that correctly, now we can start adding things up. Now, one thing that I want to do before I do that, kind of lead into this problem is, okay, here's the spots where we would be concerned about zero force members. Okay, we might be concerned about this spot, we might be concerned about this spot, and we might be concerned about this spot. Okay, and so when we stare at this, like, let's look at this spot because it's the same as this spot. Okay, and it isn't always. Sometimes you'll get a problem where it's symmetric, but they remove this force. Okay, and then there's a difference between these two spots. So, just be careful. Make sure that it's actually symmetric. So everything is the same on the left as it is on the right. So when we look at this spot, okay, I want to think about the possibilities for these forces. I'll do this in green. Let's imagine this is pulling to the right. This is pulling to the left. Okay, and I have an imaginary coordinate system that is kind of in this direction and that direction. Okay. So then we want to think about, well, what about this force? Well, it could be pulling or pushing, whatever. Is there anything to resist it, or to go in this direction? And it turns out that yes, there is. There's more than one force that has a component in that direction, because we've got this 10.5 Newton that's being applied. So this member right here is not a zero force member. It exists and it's important. Okay. And you could think about it really as taking this 10.5 kilonewton force, and some of that is going to be held. Well, it's transferring that force down here into this joint, where a lot of it is going to be picked up in that direction by that member there. Okay. On the other hand, if we look at this one, okay, so we look here, and so I'm going to imagine my coordinate system is in fact the usual XY. Okay, whatever these are doing in this direction, let's just imagine that they're both pulling on that joint. Anything that this thing does, whether it's pulling up, if it's pulling up, these cannot resist because they're only in the X direction, which means that this force cannot exist. Okay, so in essence, we could come in here and right off the bat, if we're smart, if we see that, we can erase this member. We can say, you know what, that member is not doing anything. Let's get rid of it. Okay. Now there are some reasons to have that. Not they'll show up as you guys move further down the path. But so what I'm going to do when I solve this, though, is I'm going to assume that you didn't notice that, and so we're going to leave it in. Okay. And what's going to happen is as we work our way through, we'll get to a point and you'll see that this thing is going to just mathematically come out to zero. So it's usually not the end of the world if you don't spot these, but if you do spot them, it just saves you some time. Okay. And the more you do these, the more they kind of can become second nature. I'm going to try to erase some of this work so that it's not all over my beautiful drawing here. So anyway.
I have a question.
Yes.
So they just exist for like if this ever had to bear
Go ahead.
the weight or something? Like you said it would come up
Wait, what?
further
Go
down
ahead.
the line. You said it would come up further in the class, but is that member there for like if this ever had to bear weight or something? I'm just trying to figure out why they put them in the drawing.
yeah. So there.
You froze for a second. From it might be my computer.
Because zero is like at this point. First of all, these beams have no weight. So yeah. So if this beam had a weight and it had a little distributed force coming down here, okay. So like then yes, in that case, obviously there is some weight that this beam would have to support. The other thing that happens, and I'll let you guys learn this from Agaselli because he's the structures guy. I primarily teach fluid mechanics. Is what will happen here is so let's imagine you have a member and it's in compression, so it's being squeezed from two sides. So this is when you start getting into a little bit more of like the internals. For this beam to fail, it can technically crush, but it can also do this like that, and it'll bend it. Like if you imagine this was a yardstick and you squeezed it like that, you can imagine it kind of bowing out and then splitting right in here somewhere, right? And so what this beam can do is if that beam is right here, is it basically will prevent it from failing in that way, because now this beam has to remain straight. So instead what happens is if you put that beam there for it to fail, it could still crush. And I think concrete's very strong in compression, so I think it's pretty rare for these things to crush. But it could, now it has to bow out this way, okay, which requires a lot more force. I think that requires 4 times as much force to cause it to buckle. And there's really some really beautiful solutions here that when you get to there that I remember quite enjoying. I'd have to review that to teach it to you, but luckily luckily we're not doing that right now. But that's the idea. So there are some reasons for it, but
That helps. Thank you.
yeah, it's basically beyond the scope of this class. So I like to say beyond the scope of this class. So you will learn that eventually. It's just not for me to teach you that. But I think for now, what you think is you say, well, okay, this maybe in reality this isn't a zero force member, but it's a very weak member. Like it doesn't really need to be very strong. And so so there's that. So I saw that. Yes, I didn't bring enough coffee. In fact, yes, mine was decaf, so I don't go crazy like I did a few weeks ago or last week or whatever that was. All right, so let's go ahead and start solving this sucker, and we're gonna look for the weak links here. Okay, so so this one, I've got 20.2 up. I've got 5.7. So we're gonna look at joint A, and I wish I could zoom in, but here we go. We've got 20.2 up and 5.7 down, which means that at 15.5, right? Hopefully you can see that. So the difference between this one and this one is 14.5 up, which means that this one right here has to go downwards because it's the only negative, it's the only downward force, which means it has to be upwards right here. So this one is in compression, and we know that, and this is always kind of hard to draw, but we know that it's 14.7 down. 14.5 kilonewtons down. Okay. Please interrupt me if you don't see that. Okay, so what I'm going to do real quick then is, now that I've done that, I'm going to go ahead and solve for its triangle. Okay, because every force has a triangle. And this triangle looks like this. 14.5 here, kilonewtons. We've got an angle of 18.92. Okay. And now I'm going to just solve for the other sides. And so what we'll do is we'll go and get the hypotenuse. We care about the hypotenuse really because that's what the problem asks for. But the most useful thing is this one, because that one's going to help us walk through the rest of the truss. Okay, so, but it doesn't matter because we're going to get both. We're going to get both of these. So to get the hypotenuse, let's do a sine. The sine of 18.925 equals the opposite, 14.5 over the hypotenuse. So hypotenuse is 14.5 divided by the sine of that angle. The sine of 18.925. Okay, so 53 sum. What is that, Rye? Please, guys, please don't use the chat. I can't keep up with those. So this is 44.708, unless I made an error. And then we go ahead and get this this side right here by doing, let's go back to this one. So we'll do a tangent. So say the tangent of 18.925 equals opposite over adjacent. So 14.5 over the adjacent. So the adjacent equals 14.5 divided by the tangent of 18.925. Oh, that's interesting. 42.291. So 42.291 kilonewtons. Okay, I'm gonna go ahead and check that because that seems a little off to me. So let's do 42.291 squared plus 14.5 squared. Take the square root of that. 44.708. Okay, so it's probably correct. Okay, so yeah, so as you work, it's always a good idea to check your triangles by just doing a little Pythagorean theorem. Okay, so now I can go back over here and I know that this is going off to the right at 42.291. Sorry, it's a little ugly. And I'll go ahead and write this force as 44.708 kilonewtons. Okay, but what's nice here is I know the components of this. And the reason that I want to keep the components is because I've done the y's on here, and I want to do the x's. And I know it's got this force of 42.291 coming in, pushing to the right. So that means right here, this has to push to the left. Okay, because I'm doing sum of forces. I'm just kind of doing it in my head, right? 42.291 kilonewtons. And it's kind of using like some common sense about how these things work and, that sort of thing. Okay. So I can take those forces and I can go right here and right here because they're going in the opposite direction. Because now I have to move on, right? So I either need to do this joint or I need to do this joint. I've been circling joints in red, so let's keep circling joints in red. Okay. And neither of these joints looks particularly easy. And that is problematic, isn't it? Hold on, let me clean this up a little bit because we don't know which directions these are going to go in. Okay, so let's see, how are we going to do this? This is a challenge. All right, so let's just go ahead and look at B and let's see what we can reason out. Okay, this might actually become a little complicated. I can see that potential. Let's see. Okay. So in B, well, it looks like the easiest thing here. So in the y direction. Okay, so in the y direction, I've got this negative. I've got this 10.5. I've got this 14.5 going up. Okay, and then I've got a y here, which I don't know which direction it is. It feels like it's going to go this way, but I don't know. And I've got this one, right? So I've got two unknowns in the y direction. So we're not going to do the y direction first. But the x direction is actually quite simple, right? The only x force we have is the x component of this 44.708. Okay, which I know from my triangle, which unfortunately I erased, is 42.297. That's the only x direction force on this. So I know that this force right here is going to be compressive, and I know the x component of it is going to be this 42.291. Okay, because it has to because I've got an x component here. Hello, Rocky. You're a beautiful dog. You're a beautiful dog. I'm sorry, but we're doing class right now. We're doing class. I know you want to learn statics, which you're not that smart yet. Sorry. Rocky's the only one I will call stupid. but I mean it in a loving way. All right, so so that means that our x component here has to be the opposite of this x component, and it's got the same angle. So I know that this side is going to be the same. It's 44.708 kilonewtons. Well, that simplifies things greatly, doesn't it? Because here, let me draw that force triangle over here, because it's going to be easier than trying to see all my noise down here. Okay, that force triangle is 44.708 on the diagonal, 42.291 on the horizontal, and 14.5 on the vertical. Okay, so that's like really quite helpful. Okay, so I'm not going to draw all that here. I'm just going to like keep track of that. The components of that one are right here. Okay, now the cool thing about that is these two forces right here, this one right here and this one right here, well, they work opposite each other, so I can almost ignore them in my calculations, which means this 10.5 that's being added on right here, well, it has to be directly countered by this 10.5. There has to be 10.5 right here pushing back. Okay, 10.5, wait, we've been doing red for that. 10.5 kilonewtons. Okay, so that's a compressive 10.5. And, you know, kind of as I said earlier, I mean, I was just guessing really, because I hadn't really thought about it, but this is being transferred directly to joint C. Okay, now we get down to joint C, and well, let's see, what is the easier direction here? Well, in the x direction, okay, again, I'm going to make an assumption. This may or may not be true. I'm going to assume, well, this was in tension, so I'm going to assume that this is pulling. Let's imagine this is pulling. So in the x direction, I've got maybe a force here. Also got a force along here. I don't know what direction that's going to be going, so I'm just making this up. So the x direction is not the easier direction here. That's two unknowns, right? You know, we got two unknowns in the x direction. However, in the y direction, it's always helpful to always think in terms of unknowns. We've just got this one force right here. Okay, that's the only unknown in the y direction. Okay, and we know essentially that this force, okay, it's basically going to be like this and like this, but the vertical component of it, right, it has to counter the only vertical force on this joint, which is at 10.5. So the vertical force of this is 10.5 kilonewtons. I hope y'all are following. Nobody's saying anything. I'm hoping I'm making some sense. I mean, I know we're working through it, but that
Just listening.
Okay. So here we go. So here's a little force triangle. Okay. And again, I know I've got 10.5 going up. And so now we need to solve for the rest of that triangle. Okay, so I know I've got 36.870 right here. Okay. And so, I mean, this is the exact calculation we did a second ago. It's just a different angle and different number. So let's see. So to get the hypotenuse, we'll use sine. So sine of 36.870 equals the opposite, 10.5 over the hypotenuse. So hypotenuse equals 10.5 divided by the sine of whatever that number is. So let's see here. 10.5. Hey. Is he friendly? Oh, well, if you want to come say hello, he's totally nice. He's just very noisy. Oh, look at that. That is a beautiful German. Say hello, Rocky dog. Be nice. That's Rocky. He's Dakota. Oh, hi, Dakota. Rocky's eating a few children already, so he's, you know, nice and calm. He's full. Okay, so anyway, this is one of the beauties and drawbacks to, you know, the coffee shop. I shouldn't have brought the dog, maybe. Except, you know, he's so wonderful. So anyway, so this side becomes hey, shh. That puppy's going inside. You're remaining outside. I don't have any treats for you. Okay, so 17.4999, so 17.500. And then we're going to use the tangent of 36.870. We'll opposite 0.5 over A. So A equals 10.5 by tangents of 36.870. Oh, it's a nice pretty number. 14.0. 14.000. Okay. And so that's nice. Okay, so and again, I like to check those numbers. So I'm gonna do 14 squared, 14, because it doesn't take very long to do it. And it's nice to know or feel confident about your numbers when you turn in your test. So we're gonna raise that to the half power, do 17.5. So if you do a quick Pythagorean theorem on this, it all works out. Okay. So now that we got that, I know that this angle is 17.5. So here's my 17.5. Let's do it in red. So 17.5, which means I know we've got 17.5 right here. And that 17.5 is, 10.5 down, 14 to the right. Okay. So now I can go down to this joint C and I can think about all of my X forces there. Okay. And I'm actually going to write this one out because it's we're starting to get a lot of forces in there. Okay. And it looks like I've got this force, negative 42.291 newtons to the left. I've got this one going this way, which from my force triangle over here is 14.00. So that's a positive 14.000. These are kilonewtons. I've been making that error this whole time. And then we've got this force CE, which we don't know what it is. Okay, so let's see. So here's CE right here. I'm going to assume that it's going in that direction. So we're going to say plus CE equals 0. Okay, and so CE equals, 42 point whatever. So that's 28.291 kilonewtons. Okay. So I can say this is 28, let's see in red, 28.291 kilonewtons. And then we've got this right here. Okay. Now from there, I can do symmetry through the rest. Boom. I could just kind of basically copy these numbers over, 28.291. And this one's going to be 17.5, et cetera, et cetera. And you could basically just, copy the mirror image over. But before we do that, what we want to do is we want to check all of this by going to this joint right here and making sure that everything works as we say. By the way, this becomes a zero force member by just solving it, right? So if we go to that joint right there, hold on, I'm going to erase this.
Wait, sorry, why is CE not 14?
Oh, hold on. Let me undo all those erasers. Why is CE not 14?
Yeah.
Did I do the math wrong?
Well, the 14 is what you get in the force triangle, right?
The 14 is what I get where? Sorry.
Is that it's the component of the force triangle, but I feel like there's another step in there that I just kind of missed.
Okay, let's see. Let's draw that joint all the way out. Yeah, because I'm kind of doing this fairly shorthand. I'm doing this quickly.
Yeah.
Right. So let's see. So we've got this force right here, and that's a 17.5 going off this way.
Mm-hmm.
We've got this force going this way, which is unknown. We've got this one, which doesn't matter in the X direction, but we'll go ahead and, for completeness, we'll say that's 10.5. And then we've got this one going this way, which is 42.291, right?
Mm-hmm.
Okay. So then the 17.5, that's the only one that's not in a pure X or pure Y. So we're going to use its little force triangle. So we've got a 14 here, and we've got 10.5 here. Okay.
Okay. So 14 is just the component of that force, not the force going in that direction.
Right.
I missed.
Yeah. So to make that all work out, this needs to be 28.291.
Gotcha. Okay. Thank you.
Okay. Yeah. So ideally, for me on a sheet of paper, it's like what my brain is doing is it's mentally drawing free body diagrams. It's almost like kind of like if you were on your phone and you could take your fingers and zoom in on this. Like you could put a finger here and a finger here and just spread it, you know? And I'm just kind of doing that mentally. Okay, so, all right. So if we do this all via symmetry, okay, then up here, I've got a force like this. Okay, and this is 44.708, okay? And what we want to do is we want to make sure that all of these forces coming into this last thing right here are going to work out, okay? And what's nice in this case is it requires almost nothing to do that, because the vertical component of this one, well, actually, that's not true, is it? Okay, interesting. Okay, sorry. These two have vertical components of 14.5. So we've got two 14.5s going upwards into this D joint right here. So if I do the sum of f of x, excuse me, f of y in joint D, I've got 14.5 going up twice, 2 times 14.5. And then I've got coming down, I've got the vertical components of this one right here twice. So those are the vertical components of this 17.5. So what's that? That's 10.5. So we could say minus, because those are going downwards, 2 of those, 10.5 kilonewtons. Okay, it looks like it's not going to balance, but we've also got this applied force, this external force, 8 kilonewtons, minus 8 kilonewtons. And all of that should go to 0. These absolutely required, although I require it, but if you have time, by all means, no question, you should do it. Go into the last joint, because when you get to the last joint, you should know everything. And go into that last joint and go ahead and solve it. And if we did this, we're going to go ahead and get 29 kilonewtons minus, what's that, 21 kilonewtons minus 8 kilonewtons equals 0. And that's really a question mark. And since it works out and we give that a check, we know that we've done this well. Okay. The only thing I didn't do here was, I guess, was that zero force member, which we figured out from the beginning. But the way that you do that is you look at this joint right here, and you note that you've got X. Right. That is a very nice noise. Hey, but not the barking. Hey, not the barking. Hey, shh, come here. Come here. Hey, come here. Come here. I know you love that. I know you love it. Come here. Come here. Come here. Come here. Come see. Come see. Get on my lap. Come here. Come on. Come on. You can come up. Come on. Okay. Good boy. Good boy. Come on. Come on. Good boy. All right. So yeah. So the way we do that is you do the sum of the forces in the X here. Okay. These are the only ones that can give you this component. And then the Y component, this is the only one. And because it's the only one, it has to be a 0. Okay. So that's that. Okay, Rocky dog. You want coffee? Here, drink my coffee. Okay. So anyway, I don't know if y'all can see this madness, but so any questions? Okay, this is basically me working a truss, how I work trusses. Oh my God, is that really necessary? I'm not really a fan of horns. Anyway, let's see if we don't have a lot of time. Let's see if there's something I can do here that will be useful, maybe not so long.
Do homework 7.
What's that?
Could you do homework 7?
It may be my internet. I'm having a hard time understanding you.
Could you do homework 7?
Did you say number 7? Right, did you say number 7? Oh, homework 7. Okay, let's find homework 7 here. Okay.
Oh, also, I have a question about the homeworks. I saw like we have to do homework 8, but I didn't find the assignment. Did you submit
Oh,
it yet?
I haven't posted. I posted the connect portion, but I haven't posted the problem yet. I know what I want to do. I just haven't done it yet. Wait, homework 7. Wait, Mohammed, you're asking about homework 8, right?
Yes, sir. I'm asking about homework 8.
Oh yeah, I haven't
didn't
posted
see
the
it,
assignment yet. I haven't posted the assignment yet. I haven't posted the connect portion of it, but not the written portion. And I know what I want to do for the written portion. I just haven't sat down and kind of scribbled it out. But I'll scribble it out probably tonight. It actually won't take very. I might make you guys draw it out, because I asked my class last semester to draw it out. I didn't realize how many of them were not very good at plotting functions. So and do that. Anyway.
Okay, great.
Homework
Thank
7.
you.
Yeah. So, Rai, you asked about homework 7. Can you tell me, was there a particular problem on homework 7 that you wanted me to work? Rai, anything in particular?
I'm assuming he means the PDF, the like written homework, not.
Okay.
the-
All right. We'll do that. Okay. I guess that's a good
I
one for me to
appreciate
work.
that. I'm
because-
sorry.
Which one?
Yeah, that exact one she said.
Okay. Okay. Let me bring it up. Let's see here. Assignments. Okay. 7 trusses. Okay. So a hard thing about this one, well, first of all, by having lots of different forces. So the one we just did, and a lot of them, especially if they have a nice regular geometric shape, you'll see like the forces. If you can just keep track of your X's and your Y's, they'll just kind of like grow through the problem.
Yeah, that's how I solved
Or
it.
not
I solved for one.
kind of transfer.
I kind of just solved one of the triangles.
Yeah. Now this one's interesting because, because of the external forces, things will change as you move on, but it's almost like you're adding an 80 kilonewtons to the vertical component, or 60 kilonewtons to the X component, or whatever. Okay, we've got a roller right here. I'm just going to go ahead and make the roller into a free body here. And then the G is going to have X, and it looks like it's going to have Y in this direction. We've got 100 kilonewtons going down here. Okay. So let's, what do we got? 6 meters everywhere. So this is 6 meters. This is 6 meters. This is 6 meters. And that's 6 meters. Okay. All right. So, I'm assuming the external force is solved for at this point. Okay. My hope is no, but if you do, it's fine. We can do it real quick. If not, can somebody tell me what the externals are? This is obviously 60 kilonewtons. Anybody want to tell me what the externals are? Okay, if not, I'm just going to go ahead and start working. This is C. This is G.
6. What do you mean? Excel.
What is the question? B, it was 60. Yeah. So
What is C and what is G?
C is 140.
Okay.
Oh, I get what you're trying to say. Yeah,
And,
it's 40,
yeah.
60, and 6.
66 right here.
No.
Okay.
Let me see.
No, G actually
Is that
they
right?
didn't give it to us.
Well,
G
I
is
know,
not
but I'm
fine.
trying to save
Yeah.
time. I'm assuming you guys want to work the truss and not, we've got 13 minutes. And I'm assuming you guys want to work the truss and not watch me solve the externals. Okay, I'll just solve the externals. It's totally fine. Okay, so this one is obvious because it's the only force in the X. Okay, in the Y direction, we've got negative 40 kilonewtons, minus 80 kilonewtons, minus 100 kilonewtons. And this is C and this is G, plus C plus G equals 0. Okay. So that's the sum of the forces in the Y. Sum of the moments around point G equals 0. I'm choosing G because it gets rid of some forces for me. Okay, so we've got 40. I'm going to get rid of the units right now for space concerns. So we're gonna go, what's that, 40, that's 18 meters away. Okay, and it looks like that one's gonna be going, is that counterclockwise, so we'll call that positive, plus C times 12. That's going clockwise. And then the 100 plus 100 times 6. Okay, because that's going in this direction. Then we're going to deal with this 80. Okay, so 80 is going to cause things to go this way. So that's, is that a negative? No, it's a positive 80 plus 80. And this is going to be 3. It's going to be 9 meters. And then we've got 60 kilonewtons right here coming through. So it's going to have a 6 meter thing, and it's going to cause things to spin this way. So that's going to be a negative 60 times 6 meters. And that's going to all add up to 0. Okay, hopefully I didn't miss any. See here, 1, 2, 3, 4, 5 forces. Okay, so I didn't miss any. So let's go 40 times 18 plus 600 plus 720 minus 360 equals, and we'll divide by 12. So C equals 140 kilonewtons. And if I plug that back in over here, G equals, so we've got 140 minus 100 minus 80 minus 40. So G is 80. Okay, cool. All right, so C is 80. And G is, sorry, got that wrong. C is 140. G is 80. Okay, please interrupt me if something doesn't make sense. I'm gonna go ahead and erase all this because it's in the way. All right, so what are we looking for? We're looking for BC, BD, and AC. Okay, hopefully there's a line we can draw that will cut all of those. I think there probably will be. Okay, let's see here. BD is here. BC is here. And AC. So if we're lucky, there's a way we can cut it right through there. Ideally, we'd be able to cut this like this, which means, of course, then if we can cut it like that, we don't even care about that force anymore, which is awfully nice. So we will cut it right there. And so I'm going to eliminate the entire rest of this drawing, except for that 6 meters, because that might be, useful. So we're going to pretend all of this doesn't exist. But where we cut away the rest of the world, we will replace it with forces. Okay, so let's see what we can do here. This force no longer exists because it's external to our system. Okay, and let's see, let's one here, and there's cut. Let's erase this one, and it goes to here, and that's where it is cut. Let's erase this one, and it goes to here, and that's where it is cut. Yes, I know, my whiner pup. I know. There's nothing I can do about it. You've made a real mess. You're disgusting. You disgust me. All right, in a good way. I love you. Okay, so let's go ahead and name these guys. I don't know which way should we assume? Should we assume compression or tension, my boy? Okay, Rocky thinks we should assume compression. So we'll go this way, and we'll go this way. Oh, we didn't even need those external forces. Well, that's interesting. Okay, so we're going to assume that they look like this. Oh, sorry. Oh, Rocky, get down. Get. Sorry. He's a filthy animal. Okay. I mean that in a good way. Okay. Somebody's going to call PETA on me. Okay, so this is AC. This is BC. And this is BD. Okay. And, oh, okay, that's fine. Okay. Yeah, he can absolutely have water. Okay, so what we're gonna do here is we're looking for low-hanging fruit. So, you know, we already know we have three equations. Sum of the forces in the x equals 0. We're just gonna remember that this is 6 meters, putting it over here. Sum of the forces in the y equals 0. And then really the superpowered one is the sum of the moments in the z direction equals 0. And it's just always about figuring out where do you want that force to be, okay? And so if I'm solving this, okay, in the x direction, well, just to note what we have in unknowns, we've got the BD is unknown, AC is unknown, and BC, the x component of BC is unknown. Okay, this is like really untenable. Like maybe we'll use it at some point, but that's no fun at all. Okay, in the y direction, we've got the BC in the y direction is our only unknown. Okay, so that one screams like solve me. Okay, so let's go ahead and do that one. Okay, so we've got let's see, BC in the y, which is going to have some sort of cosine or sine on it. That's positive. And we're going to subtract that 40 kilonewtons, and that equals 0. Because that's how we're going to get BC, like super duper easy. Okay, as long as you spot it. Okay, like, you know, not pretending that is not. Let me know if he bothers you. You seem to be enjoying him, so okay, he's a good boy. All right, so so now we've got this triangle here, and we never got that angle, and so that's a problem. And so
Hey,
here's the
Professor
issue
Wagner,
here. Yeah.
how did you go BC to get to 0? Just like that.
How did I go? What?
For your BC, right? You have negative 40 equals 0.
Yeah, BC minus 40 equals 0. So I'm summing forces in the y direction on this free body diagram.
Oh yeah.
Okay, and I only have two vertical forces:
Yeah.
the y component of BC and that negative 40 kilonewtons. But the problem is this angle isn't so simple, because I've got 6 meters here and I've got 6 meters here. The temptation is to go, oh, well, it's you know, it's a 66, it's an equilateral triangle, but it's not an equilateral triangle,
Yeah.
because this is 6 meters here. This is 3 meters here. So to get this angle, I need to do the inverse tangent of the opposite over the adjacent.
6 over 5.
6 over 3, which is 2. So the inverse tangent of that is inverse tangent of 2
So
is 63.435.
well,
Question. I hear
why is it not 6 over 5?
6 over 5. Where would the 5
Yeah.
come from?
Yeah.
I don't see a 5.
Yeah, exactly. Why do I'm seeing? I have. Oh no, I'm the 6 over 3.
Right.
Okay.
It is 6
Yeah.
over.
Yeah. Sorry.
got
Sorry.
it?
Sorry. Yeah, I got it.
Okay.
I got
No
it.
worries. No apologies.
Yeah.
No apologies.
My
We're all
3
learning.
looks like
We're
a,
all learning.
yeah. My 3 looks like a 5. That's why.
It happens. Happens to all of us.
Yeah,
Okay.
okay.
Well,
Mm.
I say that, and yet there are some of us whose handwriting is so perfect. I admit I love grading those of you with perfect handwriting, but mostly I'm
Okay.
jealous. 63.435
Yeah.
degrees, right? So we can go
Yeah.
ahead and solve that. You can say BC equals 40 divided by the sine of that angle. And my finger is now sweaty, so my phone won't unlock. Let's see here. 40 divided by 9 of 63.435. So that's 44.721 kilonewtons. Okay, and notice we had the right sign on it. So
Yeah.
it turns out it's in compression. So BC. So for the final answer would be 44.7 kilonewtons compressive, because it's pushing.
Yeah.
Okay. So then, so notice also if we go over to the sum of the moments in the z direction, if I choose the right spot, and this is the right spot right here, then I only have one force to deal with, and that's BD. Okay, there are other places you could choose. You could actually, you know what, this would also be the right spot. Either one of those would be fine. So if we choose up here, then we'd be solving for AC, because that would be the only unknown. If we choose down here, we're solving for BD as the only unknown. So we don't even ever have to use this sum of forces in the X if we don't want to. Okay, I'm inclined not to use it. Let's see, you know what? The easiest one is actually going to be right here. Because if we go right there, then I have no forces except for AC in this 40 newtons, kilonewtons right here. Okay, so let's go ahead and do it at, where's that? That's point B. Point B. Okay, so this force goes away, this force goes away, this force goes away. I'm left with AC times its moment arm, which is 6 meters. And then let's see, that force would be going clockwise. That's a negative. And then we've got this 40 kilonewtons. And its moment arm is 3 meters. And it looks like it's going counterclockwise. So that's going to be a positive, equals 0. Okay. And so what's that? That's going to be 120 divided by 6. So AC equals 20 kilonewtons. And it looks, hey. So again, we chose the right sign. It is in fact. So we'll go ahead and, okay. And if we wanted 3 sig figs, we could put a little 0 on there. Okay. And then what's cool here is we can do another moment. We can, at this point, I can solve either equation. Like I can plug both of these into this equation after I create it, or I can just do another sum of the moments equation, which is how I'm going to do it this time because I mentally was very excited about using this point. So I'm going to go ahead and use that point. I think that's point C. That is point C. Rocky, shut up. Hey, come here. Come here. Stop all that. Okay, equals 0. Okay, and it looks like we've got 60 kilonewtons. Okay, moment arm of 6 meters. Okay, and those are going clockwise. That's a negative. Okay, plus BD, that's same 6 meters. Okay, and then we've got that 40. So 40 kilonewtons. Hey, shut up. Come here. You're really being annoying. Come here. Come here. We're in the stretch run here. I want you to listen to me and understand. The class is almost over. Okay, and this one also has that 6 meter. Okay, and then that one is causing things to spin. That's counter. So we'll call that plus equals 0. Okay, so then we just got to solve that. So this is negative 360. That's positive 240. So it adds up to, what's that? That's negative 120. Brought to the other side, divided by 6. BD equals 20 kilonewtons. Okay, and again, we chose the right sign. How did we keep choosing the right sign here? That's really amazing. How can BD possibly be compressive? Oh, it's because of this is pushing. Okay. Okay, so one thing that we could check here, if we wanted to check all this out, is we could easily go back and do this particular thing right here. You know, the sum of forces in the X to see if we did it right. And I'll go ahead and do that because this is making me nervous. So we just need the X component of this to make this easy. The X component of that is, well, we'll just go ahead and put it into the equation. So we've got 60 kilonewtons to the right minus BD minus BCX minus AC equals 0. Okay, so 60 kilonewtons minus what's BD minus 20 kilonewtons. BCX minus 44.721 kilonewtons minus AC 20 equals 0. Oh, I forgot my angle in there, didn't I? Cosine of 63.435 degrees. Okay. So it should be obvious that, you know, 44.721 cosine 63.435 should be 20. 63.435 equals 19.9999. So this is 20. So this checks out. Okay, so that means we should feel pretty good about this solution. Okay, I'm a minute over. Apologize for the dog barking, the external noise, all that other stuff. I'll be back in my apartment with sound, and we will work this. So Any questions? We will work centroids next time. Okay, well, hopefully I will do better and I will have a better,
When's the next exam?
setup for you guys next class. So have a good day. Take care of yourselves. As always, remember, statics is cool, but you guys are cooler. So take care of yourself. Okay, what is the 12th? What is that? Where do I? Oh, when is the next exam? Yes, it's on the 12th, right? It is a week from today. So I guess next class I will do centroids unless somebody wants something they want to work on for the test. So I will bring some centroid problems, and you guys, either if you have something you're studying for, we can work that instead. That's totally fine. So yeah.
Thank you.
All right, thanks guys. I'm gonna go ahead and log off because I'm also almost out of juice here. So be easy. Let's see, meeting, disconnect, no, stop recording, stop.